Hi everyone, this is Nadia Devi. I am going to explain about Maxwell's equation. So there are four Maxwell's equation. First, I will explain about first Maxwell equation. Maxwell's first equation is derived from Faraday's law. So as you all know, we have to write the equation from Faraday's law. Faraday's law states that the induced EMF is denoted by letter V. V is the induced EMF. Induced EMF in any closed path is equal to rate of change of magnetic flux linkage in that circuit. Okay, that is Faraday's law. So the induced EMF is denoted by V, the rate of change is denoted by d by dt, and the flux linkage is denoted by phi. Okay, Faraday's law statement is induced EMF in any closed path is equal to rate of change of magnetic flux linkage in that closed circuit. Okay, this negative sign indicates the induced EMF opposes the flux produced in that circuit. So this is the equation number 1. Now, in general, the induced EMF, that is potential, is equal to the relation between potential and electric field intensity is denoted by V equal to closed integral of E dot dl. That is, the potential available in a circuit is equal to the electric field intensity around a closed path. That's why closed integral of E dot dl is denoted. So now we got the two equations of EMF. One is minus d phi by dt, another one is closed integral of E dot dl. Next, as per Gauss law, according to Gauss law of magnetic field, the magnetic flux, phi is magnetic flux. Magnetic flux can be written as closed integral of B dot ds, where B is magnetic flux density. Now, we can equate equation number 1 and 2. So, because equation number 1 and 2 both have LHS as induced EMF V. Therefore, we can equate equation number 1 and 2. By equating equation 1 and 2, we can write closed integral of E dot dl equal to minus d phi by dt. Now, we know the value of phi. Equation for phi, magnetic flux equation, can be written as closed integral of B dot ds. Okay. So, now by applying time varying field, so in case this signal is varying with respect to time, if the signal is continuously varying with respect to time, we can write d by dt as dou by dou t. So therefore, the equation number 4, that is closed integral of E dot dl, can be written as minus integral of dou b by dou t dot ds, where ds is differential surface. This equation is Maxwell's first equation in integral form. Now, we have to apply Stokes' theorem in your LHS side of equation 5. So, Stokes' theorem relates line integral and surface integral. So, general equation of Stokes' theorem is closed integral of A dot dl equal to surface integral of del cross A vector ds. So, now we can apply Stokes' theorem in your LHS side. So, if you apply Stokes' theorem in your LHS side, the equation of LHS side becomes del cross E vector dot ds. This is a surface integral of del cross E vector dot ds, which is equal to the RHS side will be same as it is, that is minus dou b by dou t dot ds. Now ds is common in both LHS side and RHS side. So we can cancel on both sides. The remaining equation will be del cross E vector equal to minus dou b by dou t. This is the Maxwell's equation in differential form. Maxwell's second equation is derived from Ampere's law. The Ampere's law states that the magnetic field intensity around a closed path is equal to total current enclosed in that path. So, the point form or differential form of Ampere's law can be written as del cross H vector equal to J, where J is current density. Now we have to take divergence on both sides of the equation number 7. So if you take divergence, the equation becomes del dot del cross H vector, which is equal to del dot J vector. Now, according to null identity, divergence of a curl of a vector is 0. So as per the null identity, we can write del dot del cross vector equal to 0, and it is also equated to del dot J vector. But according to the equation of continuity, we know the value of del dot J vector. That is, del dot J vector can be written as minus dou rho v by dou t. Okay. From equation number 8, we obtained del dot J vector equal to 0. But this is not an acceptable situation. So it is unrealistic situation. For a time varying field, the equation number 7 can be written as by adding a temporary variable by adding a term JD, where JD is displacement current density. By adding a temporary variable JD in equation number 7. Now we have to take divergence on the equation number 9 on both sides. If you take divergence, it will become del dot del cross H vector, which is equal to del dot J vector plus del dot JD. Now, as per null identity, we can write the divergence of a curl of a vector is 0, which is equal to del dot J vector plus del dot JD. Now we know the value of del dot J vector from the equation of continuity, that is minus dou rho v by dou t plus del dot JD vector. From this equation we will get the value of del dot JD. So del dot JD equal to minus dou rho v by dou t. Now from point form of Gauss law, we will obtain the equation in terms of rho v. So del dot D vector equal to rho v. This is the differential form or point form of Gauss law of electric field. Now we will substitute the value of rho v over here. Now by substituting the value of del dot D vector equal to rho v. So instead of rho v, we can substitute del dot D vector in equation number 10. Now we obtain del dot JD equal to del dot dou rho d by dou t, where d is electric flux density. Now by equating those two equations, del dot JD equal to del dot dou d by dou t, we will write JD vector equal to dou d by dou t, where d is electric flux density, JD is displacement current density. Now substitute the value of JD in equation number 9. That is, equation number 9 is del cross H vector equal to J plus JD. We obtain the value of JD. JD is dou D by dou T, right? So this is the equation in differential form. Maxwell's equation in differential form. Now we have to write the Maxwell's equation in integral form. So I have written Maxwell's second equation in integral form can be obtained by taking surface integral on both sides of equation number 12. So Maxwell's equation, second equation in integral form is obtained by taking surface integral. So write del cross H vector ds equal to integral of J plus dou d by dou t ds. Now we can apply Stokes theorem on your LHS side. So if you apply Stokes theorem, we can obtain the equation integral of H dot dl equal to integral of J plus dou d by dou t ds. This is the Maxwell's second equation in integral form. Now Maxwell's third equation is obtained or derived from Gauss law of electric field. Gauss law of electric field states that the electric flux density in a closed surface is equal to total charge enclosed in that surface. So we can write the equation as integral of d dot ds equal to q. Q can also be equated to integral of rho v dv, where rho v is volume charge density. Volume charge density is defined as the total charge available in a given volume. Therefore, Q can also be written as integral of rho v dv. So this is the equation integral of d dot ds equal to integral of rho v dv. This is the Maxwell's third equation in integral form. To obtain the Maxwell's third equation in differential form, we have to take divergence on the LHS side. Divergence, to obtain the Maxwell's third equation in differential form, we have to take divergence theorem on LHS side. If you apply divergence theorem on LHS side, del dot d vector dv equal to integral of rho v dv. Here dv is in volume integral is common on both sides, so we can write del dot d vector equal to rho v. This is the Maxwell's third equation in differential form. The last Maxwell equation, Maxwell's fourth equation, is derived from Gauss law of magnetic field. Maxwell's Gauss law of magnetic field is closed integral of B dot ds equal to 0. That is, magnetic flux density around a closed surface is equal to 0. This is your Maxwell's fourth equation in integral form. Now apply divergence theorem on LHS side. We will get del dot B vector dv equal to 0. Therefore, we can write del dot B vector equal to 0. This is Maxwell's fourth equation in differential form. So, there are four Maxwell's equation. First Maxwell equation is derived from Faraday's law. Second Maxwell's equation is derived from Ampere's law. Third Maxwell equation is derived from Gauss law of electric field. Fourth Maxwell equation is derived from Gauss law of magnetic field.